Hi, this is the second half of the video lecture for Chapter 6 on chemical equilibrium from Harris's Quantitative Chemical Analysis, 9th edition. We're going to be finishing by talking about acids and bases. We're going to talk about common ion. We're going to talk about complexes and the formations of complexes. And we're just going to wrap up at the end with just a brief description of polyprotic acids and bases and what their equilibrium expressions look like. So let's start with the common ion effect. And we need to start with the definition first. That is, that understanding that a salt will be less soluble if one of its constituent ions is already present in solution. We can understand this by relating it back to Le Chatelier's principle, where we understand that when we apply a stress to a chemical system, the chemical system in question will shift away from that stress to alleviate the pressure. And so it does accurately predict this because we see that when we have common ions, we might be adding an ion from a different source, and that different source is then going to affect the solubility of the ion in question. And so we're going to see that the chemical equilibrium might shift away from that. Another way to think about this, quite simply, is just to say that each individual chemical species, in this case ions, have a defined solubility, no matter what their source is. And so we might have 1, 2, 3, on any number of different sources for a particular ion, but its individual solubility remains the same regardless. So if we have two salts that have a common ion between them, in the example below we see that it's iodide, we can actually use the common ion effect to help predict and selectively precipitate out the less soluble salt if the relationship between them is significantly different in their K value. The first thing that we need to do to try and assess selective precipitation here would be identifying which of the two salts is more and which one is less soluble. In this particular case, we can look at the KSP values. These, remember, are the solubility constants. And so we see that the two of them have drastically different solubility constants. And so we can also remember that these are K equals the concentrations of the products over the reactants. And so for those that have much higher values, much larger values, then those salts are going to be more soluble. So we can quickly assess that PbI2 solid, or lead iodide, is much more soluble by about 20 orders of magnitude in relation to our mercury iodide. So then, which will precipitate first when we add extra iodide in? The answer to this one, of course, is that the mercury is going to precipitate more quickly because this is the one that has the lower solubility. And since the difference in their solubility constants is so significant, we can selectively precipitate out the mercury iodide, leaving behind the lead iodide, even though it also does not have a very significant solubility. So we did talk briefly in lecture 6a about complexes, and I just want to remind you that complexes are chemical species that have a metal center with one or more ions or molecules that are attached and surrounding them. Then I want to take a look at a series of these different equilibrium expressions, where in the reactions the capital M refers to a metal center and X refers to some ion or molecule that's a ligand that can be attached to that metal center to form a complex. So if we take a look at equilibrium expression 1 with K sub 1, we see that it goes from a metal that's individual with an individual molecule to Mx. So now this is the complex Mx. But then we can see that following that we can take Mx and we can actually form Mx2, and in a series, in some cases, we can form Mxn minus 1 or Mxn, where this number can increase sequentially. If we look through the equation in the upper right for K1 and K2, these two balanced equilibrium reactions, we can see that we can cross out chemical species that are across the equilibrium arrows on two reactions. And we can see that then we end up with an M plus 2X goes to Mx2. if you look at the expressions below, you'll note that this is rewritten here, and instead of using K1, K2, or some other K value, it's traditional for us to write these as betas, where betas are the sequential steps that we're adding together. If you remember from the beginning of Chapter 6, we did assess that some K value, where it was sequential reactions, were the products of the other K values. So when we're doing this in a computational problem, we'll actually take the two expressions on the right-hand column in the upper right, and we can multiply those to solve for beta 2. So as a quick review of this, we see that if we add the two equilibrium reactions together, we can get beta 2. And therefore, if we extend this to other sequential steps, we get beta sub n is equal to K1 times K2 times all of those K values. And then we can add those together. We can add the reactions together and multiply the K expressions to solve for new summative or sequential reactions. The interesting thing that we see playing out below is in a specific case here that we're going to take a look at. We have lead and we have iodide. And we can see that lead follows just such a scenario where we have lead iodide is a potential product, PbI2, but we can also form PbI plus and PbI3 minus and PbI4 2 minus. These are the sequential balanced equilibrium reactions on the bottom left. If we notice in the plot on the right, notice that the x-axis is the log of the iodide concentration. So from left to right, we see increasing concentration. And going up and down on the y-axis is the log of the total lead concentration. So we're talking about the sum of all of the concentrations of the various lead species. So this is how we're getting back at a couple of different things going on. This might seem a lot like the common ion. Well, as it turns out, the blue line represents the actual concentration of lead that's total in solution. And you can see that it initially, as we increase the iodide concentration, it's governed by the common ion effect. And so we see more and more of these lead species and more iodide being added, and so we see a decrease in that solubility. But then on the right-hand side, as iodide concentration increases sufficiently, we can actually break the threshold for the formation of each of these other complexes, thus reducing the amount of lead that's actually free in solution, but increasing the total amount of lead that's in solution, because now the solubility of lead isn't dictated simply by the solubility of Pb2+, because we're adding the solubility of Pb2 plus and Pbi plus and Pbi2 along with Pbi3 minus and Pbi4 2 minus. So you can see over this range of concentrations for iodide, first we see a loss of lead concentration, but then eventually when it breaks a certain threshold, we can see that increase again. And the plot is labeled to help us understand that on the left side it's governed by common ion effect, and on the right side it's governed by the complex formation that we've just talked about. So let's take a look here quickly at acids and bases. Now, I briefly introduced acid and base equilibrium expressions, but I do want to just remind you that we're going to be dealing with, in this particular class, we're going to be dealing with Bronsted-Lowry definition of acids and bases rather than the Lewis definition. So we understand acids to be proton donors, and we understand bases to be proton acceptors. And so when we set up a simple Rice table for equilibrium expression between ethylamine for the acid dissociation of the ethylamine, we can write in the following information. So we're going to start again with the balanced chemical equation. So this is our reaction row. And we're just using the information provided to see that we're seeing deprotonation of ethylamine to create its conjugate base and H+. Notice that we have both atom and charge balance from the left to the right of the expression here. Then we can fill out concentrations that we know. We're told that we start with 0.1 molar ethylamine. We know then in that instant, that snapshot of a moment before starting the rest of the reaction, we have 0 concentration of the other two species. and therefore the change in the concentration of ethylamine is minus X, while the change in the concentration of the other two species, since there's a 1-to-1 mole ratio, is plus X respectively. Now we can actually go through and add those three columns up, and we end up with algebraic values here that we'll have to solve for using a single equation and this single unknown of X. So we write our K expression substituting in our values in the bottom of our Rice table. So the K, remember, represents at equilibrium, and so we're not talking about a Q. In this case, we're taking the values from the equilibrium row of our Rice table, and we're substituting them in for the concentrations of the respective chemical species in the K expression. You can see me do that here, where we have X times X over 0.1 minus X. Then when we rearrange and solve for X, we find that X is equal to 1.46 times 10 to the negative 6th. And now we can assess whether or not it was important for us to incorporate the calculation of 0.1 molar minus X. This certainly makes the calculation a bit more complicated. If we assume that that value is negligible and repeat the calculation, we see in this case that we get X is equal to 1.46 times 10 to the negative 6th. So the same value. So in this case, it would be appropriate for us to assume that X is negligible. In class, we'll talk about when is it that we can assume it's negligible and when can we not, and we're going to take some time and try to make sure each one of us is able to use our poly solver and our regular solver on our TI calculators so that you're set up to be able to solve these simple and then following this some more complex algebraic expressions without having to do them longhand. Now that we've done a quick solution using a Rice table and a really basic acid dissociation constant, let's just review quickly pH and pOH. So hopefully you recall that when we're talking about pH, we're talking about the negative log of the H plus ion concentration, and when we're talking about pOH, we're talking about the negative log of the OH minus ion concentration. We also know that pH plus pOH is equal to 14, which is equal to the negative log of Kw. We see up above, typed into the slide, that Kw is equal to the H plus ion concentration times the OH minus concentration, and that's equal to 1.01 times 10 to the negative 14. That's at 25 degrees Celsius, and this comes from the acid dissociation / base hydrolysis balanced chemical equilibrium for water. So this is our Kw expression. We want to make sure that we're remembering these equations. These are ones that we should know inside and out without having them written on an equations sheet. So you will need to memorize these, but you'll get ample time and opportunity to use them in calculations to help reinforce that as we move through the chapter. Then I want to also remind you that we have a small list here of common strong acids and strong bases, and we generally accept that these do not exist at equilibrium. So they completely dissociate to form their ions in solution, and while these lists are not the only such lists, this is the list of both acids and bases that I want you to be familiar with. So we have hydrochloric acid, hydrobromic acid, hydroiodic, sulfuric, chloric, perchloric, and nitric for our acids. Then you'll notice in the bases we have sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Not all people consider all of these strong acids and bases, and some people consider other acids or bases to be strong. But this is the list that we'll work from for this semester, and it should serve us quite well. Now, since we're talking about strong acids and bases, it's probably essential for us to quickly review the weak acids and bases also. So if strong acids and bases completely dissociate, then the way we understand weak acids and bases is to say that they only partially dissociate in water. So for acids, this means that we have a reaction for the acid dissociation to form its conjugate base and an H plus ion. So HA is a general weak acid, is in equilibrium with H plus and A minus, its conjugate base. And we can write an equilibrium expression for this, where Ka is equal to H plus concentration times A minus concentration over HA concentration. Then for base hydrolysis, we're going to write the reaction for the base to form hydroxide from the base and water. Remember that when we're dealing with acids and bases, we always have water available to us because we're always talking about aqueous systems. So when we need to, we can just call on that water as an available reactant or product to allow us to balance our reactions. So notice here we have A minus plus water, so our weak base plus some water. Our water actually protonates the weak base, causing it to produce hydroxide. And this is how hydroxide is formed from weak bases that don't actually contain hydroxide. Our Kb is then written here, where it's equal to Ha times OH minus over A minus. And we can actually relate Ka and Kb by saying that Ka times Kb is equal to Kw. What you'll notice is that, remember, these are sequential reactions when we have a K times a K. So if we take the acid dissociation reaction as a sequence from the first step in a sequence and then add to it the base hydrolysis and cancel out left and right reactants that are on both sides, what we'll find is that HA on both sides and A minus on both sides cross out, and we're left with H2O goes to H plus OH minus, which is Kw. So by this reasoning, we can relate these to the numeric value that we gave, 1.01 times 10 to the negative 14th. And we ought to be able to use this relationship in any calculation that we see fit while we're dealing with acid-base equilibrium calculations. Finally, I want to briefly mention polyprotic acids and bases. These are acids and bases that donate or accept more than one proton. Some good examples of this include sulfuric acid, phosphoric acid, and carbonic acid. Some bases include barium hydroxide, phosphate, and sulfate. And what you might notice about the two lists that I've included here, though this is only a partial set, is that conjugate acids that are polyprotic have conjugate bases that are polyprotic. So sulfuric acid has sulfate and hydrogen sulfate. In general, we can write then a series of acid dissociation and base hydrolysis reactions for any polyprotic acid-base conjugate set. So for H3A, we can write Ka1 is equal to H2A minus plus H plus. And then we can further dissociate H2A minus to Ha2 minus, and then once again to A3 minus. The thing you'll notice here is that we start at the top with Ka1, but the reverse of this is not Kb1. We start on the other end of this series of reactions with the strongest base to establish that is Kb1, and the strongest acid to establish that is Ka1. So they run in opposite orders. It's also important to note then, by extension of our previous slide, that Ka1 times Kb3 is equal to Kw, or 1 times 10 to the negative 14th. And similar expressions can be written for each of these sequential steps, understanding that if we pair them, Ka and Kb, we're left with H2O goes to H plus OH minus. Now we're certainly going to talk at more depth about acids and bases and the equilibrium reactions that they participate in as we move beyond Chapter 6 into Chapter 7 and beyond that even. So stay tuned, get some good practice now and become familiar with the calculations and how to set up rice tables, and we'll circle back to this later.